5.5. Use substitution, and now I will show you lots of different notations, and then you will tell me if you like it or not. We're going to start with examples. The more examples I show you, the better it gets. How to integrate cosine of x to the 4 plus 2 times 4x cubed dx. Last time I taught you shortcuts. They involve linear functions inside of the cosine or sine. This one is not linear. It's x to the 4 plus 2, and it's multiplied by 4x cubed. So you cannot use shortcut. Let's use the strong tool which we have to integrate this type of functions. Chain rule. Undoing chain rule is use substitution. The idea is we know how to integrate cosine, but not cosine of complicated stuff. So let's call this complicated stuff to be u. This is a popular notation. Call it u. And let's start the box. Let, usually we don't write let's too long, so just we know it's let u be x to the 4 plus 2. Then differentiate both sides. Du is 4x cubed dx. This notation we showed you very briefly in calculus 1 is called differentials. Du on the left and then dx on the right. It's du over dx, but rewritten in the forms of differentials. This is the box. Usually, I like this notation. Usually in the United States, they write it down this way. Around the world, it's a bit different, but the idea is the same. So we differentiate that. And now check this out. We want to rewrite this integral in terms of u. So u is x to the 4 plus 2. Here it is. So it's going to be u cosine of u. Agree? That was the whole point. We decide to substitute the complicated part with u. Now, what to do with this part? Coincidentally, this part matches with du. So that's going to be du. This will be du. I call it the tail of the integral. The tail of the integral matched with du. So it's going to be cosine u du. For now, it's magically matched. So after this, I'll show you what happens if it doesn't match. That was your question? Yeah, I guessed. It was like, I'm reading your mind. Yes. So for now, it's perfect. Cosine u du. What is the integral of cosine again? Sine plus or minus? Plus sine u. That's it. Plus c. Thank you. Now, nobody knows what u is except you. You created u. So let's go back to the original notation. U is x to the 4 plus 2. So the answer is sine x to the 4 plus 2 plus c. Put this in the box. This is the answer. This is what you will be typing in your homework web work. So nobody knows what did you do to get this answer. Nobody cares. Usually when people present results, they will ask you what method did you use, and you like use substitution, but nobody will ask you what was u, how do you find du. So the box is intermediate calculation. That's why the answer should be in terms of x. Don't forget to go back to the original variable, because people will ask you sine of u, what is u? We started with x, and that makes sense. You start with x, you finish with x. Think about some good questions, and for now, I will check. How to check that the answer is correct? Find the derivative, and the answer of the derivative should be whatever is inside of the integral. So I'm going to differentiate x to the 4 plus 2 plus c, and this is when chain rule will be involved. So we undid chain rule. Let's see. Derivative of the function outside is derivative of sine. Derivative of sine is cosine. Copy the function inside. Times. Chain rule steps in. Chain rule says look inside and differentiate the function inside. That is 4x cubed. Plus c gives you plus 0. This is exactly what we had inside of the integral. So we are undoing chain rule. I'm saying it too often, but it's just like a nice thing to understand. When we undo chain rule, we expect to see that one piece in the integral, which is this in blue, looks like a derivative of another piece of the integral, which is inside of cosine. And that's exactly how chain rule was done. the piece 4x cubed is derivative of the function inside. So that's why we choose u to be whatever is inside, and dx and du will be the tail. What do you think about that? I'm going to show you more stuff, and it gets more interesting after this. So, before I show you more stuff, let me show you the formula. Nobody remembers the formula usually. People just remember the technique. So this is not a topic when you're supposed to remember formulas. But it's called the substitution rule. Let me know if it's too small. I can zoom in. If there is a function u called, so there is a function g of x, we're gonna call it u, and this function is differentiable. What does it mean to be differentiable? You can take the derivative. Exactly, thank you. Differentiable. It's a long word. Differentiable function whose range is on I, some interval I, on I, range are outputs, if you remember, outputs. And f is continuous. Continuous means no hole, no jumps, no asymptotes. Also on I. Then u substitution looks like so. There's an integral and there's a function f which has a function g of x nested inside, not nasty, nested, like nesting dolls, Russian dolls. It's inside. Times it's multiplied by the derivative of g prime x dx. U substitution looks like so. We choose g of x to be u, then the tail becomes du times or over some constant. You were supposed to figure this out later. And it all can be rewritten as the integral of f u du. So this is the formula, and again, it's a theorem, but the result of this theorem is a technique. So nobody expects you to remember the formula. You just need to know how to do it. Most of us just know how to do it. That's it. Yes.
Sorry, I asked a lot of questions. Is that f just a normal f, or is that a special one for antiderivatives?
Oh, I know what you mean. Just a normal one.
Okay.
Yes. There was a question about antiderivatives. We had that. There was capital F, small f. We don't talk about antiderivatives anymore. We just integrate everything. But I know that we started teaching with antiderivatives. Yeah. No, good point. More examples. And now I will show you an interesting thing. Apparently, u substitution is not taught the same way in America and other countries, so I will show you two ways, and you can choose the one you like. Example 2. How to do the integral of a square root of 2x plus 1 dx. So, you might have some comment about this integral later, but let me show you the notation and technique. You don't like integrating square root of complicated stuff. So the choice of u should be this complicated stuff. That just makes sense. We know how to integrate square root of u. So let's make it to be square root of u. So the table is let u to be 2x plus 1. I don't write let anymore. Too much writing. Then also that's too much English, okay? This math is, let's get rid of English there. That's why I like to teach. That's why students whose English is a second language like my classes. I had to learn math in English, and then I learned how to teach it better to avoid English. So du is 2. 2x plus 1 gives you 2. Don't forget dx. Now look at this dilemma. We need 2x dx, but we only have dx. So we need to make 2 dx. So I do it this way. That's my favorite way, but you don't have to do it. This is my way. Since I need 2x dx, then I will multiply by 2. And now I have 2x dx. Sounds okay to me. But since you cannot just multiply by 2, I will divide by 2 outside of the integral. You can divide it right away, but I like to kick it out outside of the integral. It's just prettier this way. Then this is perfect du. See, so I made it to be perfect, and this is my table. So u, let me show you. U is 2x plus 1. Du is 2 dx. And the integral becomes 1/2 integral, can you tell me? Square root of u du. Amazing. Look at that. We know how to integrate square root of u. We did it last time in previous class. It's going to be 1/2 u to what power?
1/2.
3 halves. Exactly. So you rewrite this as u to 1/2, and then you integrate it. So 3 halves divided by 3 halves plus c. Nobody wants to see answer in terms of u. So we're going to go back to the previous notation. It will be 1/2. Let's multiply by 2/3, flipping the fraction. U raised to the 3 halves. Don't forget all of those notations when you're plugging in the original function. U is 2x plus 1. That's why this table is a very nice visual box, because then you can easily find what was u. This is the answer. Or you simplify. Cancel out 2. And you will get 1/3 2x plus 1 3 halves plus c. Put this in the box. Type it carefully in your web work. Okay, ask me 2 questions.
Sorry.
Exactly 2. Yes.
We get that 3 halves just from doing the integrating it.
Integrating. So it was 1/2 plus 1. 1/2 plus 1 is 3 halves. You do the 3 halves over 3 halves. 3 halves, yes.
So we're multiplying it by 1/2 in the beginning because we want 2 dx.
Exactly. We needed 2 dx, but we just had dx. So I multiplied by 2. But you cannot just multiply by 2, so I divided by 2 as well. That's how fast I can talk. But it makes sense, yeah. Yes?
Isn't that what you're doing it, where you have to use the true dx, you just divide by 2?
Just a second. That was a good comment, but a bit too early. So that was not a question, by the way. Oh, no, it was a question actually, yes. You said, is it? Yeah. So let me show you second way, and then you will say what you just said. That was very smart. This is way 1. I was taught this way, and I was very happy about it. And then I saw different way in America, so let me show you second way. And then you choose the one you like. Doesn't matter, they both good. Way 2. Way 2 is more popular here. So the same integral, we have a square root 2x plus 1 dx, like so. The same idea, we're realizing this is a good choice to do u inside of the square root. You're writing down, let u be 2x plus 1, exactly the same way. Du is 2 dx. And then the logic is different here. They say, you know, we need dx, so let's solve for dx. And then that's what we do. So solve for dx. So dx will be, how do I solve? Du equals 2 dx, so I'm dividing by 2. Dx will be 1/2 du. Now we have 3 equations, 1, 2, and 3. And we only use, this is my table. So the table became bigger. We're only using equation number 1. We're going to plug it inside of the square root. And equation number 3, we're going to plug it in the dx. So dx was explicitly solved with this method, way 2. And the integral becomes, check it out, integral, we still have square root of u times, and dx will be plugged as 1/2 du, and it's exactly the same integral we had before. Compare, they're both on the right. This one and this one, it's exactly the same thing, but the idea behind how we found du is different. So I will show you my example with 2 ways, and then you choose the one you like. Usually during office hours, I can see if a person stuck on the step, you use way 2. If a person's pretty fluent, use way 1, it's faster. So it kind of depends on the mindset also. It's fine, both of them are pretty good. We know how to do that. I will just write down the answer. 1/3 2x plus 1 come on, yes, 2x plus 1 raised to 3 halves plus c. The same answer. If you want to check if you're wrong, differentiate this. 3/2 goes down, multiplied by 1/3 gives you 1/2. 2x plus 1, change to power becomes 1/2 times 2 by chain rule, and you get exactly the square root of 2x plus 1. So maybe put like dot, 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 dot equals, because we just solved it already. Yes?
How do we find du?
What?
How do we find?
Oh, du?
Sorry for du or dx or?
So this is like an interesting way, complicated to explain. Let's see, let me tell you again. We chose it. Du, bless you, is 2dx. And then we just saw we have a square root of u. This piece is done. We don't need to do anything here. And then we need to change the x somehow. So we need to find the x from the equation number 2. So we solved for dx. To solve for dx, I needed to divide by 2. So I divided by 2. Here it is. And then I had dx equals, so it was like this. Dx equals 1/2 du. Same result, just a bit slower. But it's more explicit though.
And how does that go into the bottom? That's where I was going to ask. From that to that.
So, the solution, the idea exactly the same. You will have 1/2 square root of u du, and then we already did this.
Oh.
So it's exactly the same integral over here in this circle. Yeah.
Yeah.
Mm-hmm. 1/2, you can kick it out outside. That's what I always do, kick out outside the coefficient, the constant. Good questions, yes.
What if you end up with du equals 2x dx and you don't have a 2x in the integral?
We will do it. Yeah, we will do it right now.
And it's not just it's not just you multiply by 2x and divide by 2x?
No, we will do it right now. That's a good question. More complicated examples. And then when the S are going to work, we're going to learn integration by parts on Wednesday. Now, did anyone notice we learned something last time which could do this faster? That's what you said. What did you say? What did you say last time? No. Yeah, someone over there mentioned. What if we can do it which way?
Move the 2 over to the side with u.
Yeah. Oh, you said divide by 2, remember? Yes, divide by 2. We learned, what did we learn last time? Shortcuts. So let's do that. This is actually a good example of a shortcut. Good job for anyone who noticed. And good job for everyone in general. Shortcuts. If you remember, we just learned them. Those are u sub for u sub. This one can be used for this example. Ax plus b to the n dx equals ax plus b raised to the new power n plus 1 over n plus 1. And what? Divide by the leading coefficient a plus c. This is what we learned last time. One of the shortcuts. So this integral actually falls into the idea of the shortcuts. We have 2x plus 1 dx. Well, n is 1/2 then. So it's going to be 2x plus 1. 1/2 plus 1 is 3/2 divided by 3/2. And then you don't forget to divide by the leading coefficient, which is 1 over 2. This 2 is a leading coefficient a. Plus c. Let's simplify and you will see it's exactly the same answer. 1/2 times 3 times 2/3 is 1/3. 2x plus 1 to the 3/2 plus c. It's exactly the same answer but faster. Compare how much writing we did before and now. So u substitution works for everything, but shortcuts, they work for linear functions inside of square root, sine, cosine, logarithmic functions. Well, we're going to learn logarithmic functions soon, and so on. We did lots of exponential functions. So if you know shortcuts, you'll be fast on a test, but I don't require you to know it though. I will never test you on a shortcut. But if you know it, you're faster. And it's just a good feeling to be fast, with math. Let's do one more example and I will show you that shortcuts are pretty awesome again. Example number 3. Example number 3 has exponential function e to the 5x dx. We know how to use shortcut for this. Do you remember? The shortcut. Exactly, it's the same thing, and then you divide by the leading coefficient. So you first integrate the way you know, and then you divide by the leading coefficient. Because when doing chain rule says differentiate and multiply by the leading coefficient. But we are doing chain rule, so you divide. So this is shortcut. Shortcut. But now let's do long way. So e to the 5x dx equals, u should be chosen what? What do you think? 5x, thank you. Don't sleep. I can also yell in Russian, you know. Let u be 5x. du is then 5 dx. Derivative of 5x is 5. Now choose the method you like. You need 5 dx, but I have just dx. So I do multiplying by 5 and dividing by 5. Make sense? Because we need this composition, so I just made it happen. That will be perfect du. Then it will be 1 over 5 e to the u du integral. And I'm kicking out 1/5 outside. It's not necessary, but it looks better when you have constants outside. What is integral of e to the u? E to the u plus c, but nobody knows what u is except u. So plug it back. E to the 5x plus c, and this is the answer. The same answer as a shortcut, but takes longer. 1/5 e to the 5x. Basically copy, divide by the leading coefficient, but this is the full u substitution process. Yes?
So the du goes away. So 5, because you have e to the u du.
E to the u du, yes.
That goes away. Du.
So let's see.
Sorry, that's my keeping.
Let me try to explain, and you tell me if it makes sense. So it was 5d. So it was dx. I multiplied by 5 because I wanted 5 dx. This became du. Now I'm calling it e to the u du, but it's inside of the integral. When you integrate, du disappears. Yeah, makes sense. Good job. What I wanted to say is u substitution is not called like this around the world. Americans chose u as a letter, and then they use it quite a lot in calculus 3 as well and stuff like that. In different countries they do it differently, call it differently, but the method is the same. And you technically speaking can use T, M, J, first letter of your name. It doesn't matter. The method. So since you give the result in terms of x, nobody cares what did you use to do your substitution. That's my point here. Are you ready to do example by yourself? Did you pay attention? So let's do this example by yourself and then see if you get it. How would you integrate tangent? We never did that. We never integrated logarithm. We do it this week. But we also never integrated tangent before because it requires u substitution. How to integrate tangent x dx? You can work with people around you. My recommendation, if you don't know how to work with trigonometric functions, always write down a definition of it first. Maybe that will help. Tangent is what? Sine over cosine. So write this down first and then choose your u and proceed from there using examples before. Any example before. Tangent, sine or cosine, and then choose some function to be u and see if it helps. If you mess up, choose another one. Yeah, very good. Work with groups if you want. Sine or cosine, choose something to be u and it might work.
Whatever it is,
Sine squared.
sine squared.
One of those.
That's do something with what
The shortcuts over here I can show you. Here they are. These are the shortcuts. We had 5 shortcuts. It's nice if you remember them, but if you don't, you're fine. It's not too bad. Did anyone finish? Yeah, good job, people. Let's do it. So the first step, I always say, if you work with secant, tangent, cosecant, you get scared, write it down as a definition. Sine x over cosine x dx. Now what? Choose something to be u, and it's not obvious what it is. To be honest, most of the time it's not obvious, or else the exam will be too easy. So you need to figure, you will have intuition about it, but in general you choose one. Say you choose, so there are obviously only 2 things here to choose. U is either sine or u is cosine. Maybe u is like 1 over cosine. And the thing is, you choose one and then you work it out and it doesn't work. You choose another one, it doesn't work. You choose another one and it works. So being in a STEM major is basically being frustrated all the time. I was telling it to students when I was presenting about research, what it is to be a scientist in STEM. And they asked me, so when do you get this result? I said, usually you do lots of simulations, computer coding, math, and it doesn't work. Most of the time it doesn't give any results. And then when it does, you publish the article, you give presentation, you get PhD. So STEM people are trained from calculus sequence already, or coding, debugging, to be frustrated all the time. And that's why we're so grumpy all the time. It's like part of the degree you choose, or even lifestyle, or even career, you know? It becomes your mentality. So being frustrated is part of your life. So that's how you do it. You just mess up all the time, and then it works. And that's just the whole idea, how to get better. So which one did you choose? Sine, cosine, or 1 over cosine?
Cosine.
Okay, we have different opinions then. So let's see. If you choose sine, du will be cosine x. But we have 1 over cosine x, and you cannot fix that. Okay, you cannot somehow make it to be 1 over cosine x. And that's when you're stuck and it doesn't work. So I would not choose that. Besides, integral of sine is not very complicated. Integral of 1 over cosine is a troublemaker. So maybe I would choose this one to be u. If u is cosine x, then du is what? Sine or minus? Minus, be careful with that, dx. Now let's look carefully at all of those circles. So I chose, this is my box, I chose cosine to be u, so I'm kind of building 1 over u situation. I need minus sine x dx, but I have plus sine x dx. So I multiply by -1. and divide by -1. And the answer becomes, not the answer, the integral becomes minus, this minus pop out because I needed it to be there. I needed this minus. It was not there, so I did it myself. Integral of what? 1 over u du, or even du over u. So again, the hat, this hat, the tail becomes a hat in this case, is du, and then it's over u. Minus du over du. Minus integral du over u. What is integral of du over u? Natural log. It's 1 over u case, 1 over x. Integral of 1 over x is natural log. So I'll write down natural log of u, correct or not?
Plus value.
Absolute value, thank you. Absolute value is important. And again, don't leave this as the answer because you need to go back to the original variable. U is cosine, I see it in my box. So it's cosine x. Bar, go black. Bar, yes, plus c. And this is the final answer, minus logarithm of cosine plus c. What do you think about that? Before you have questions, and I'm looking over there, I'm looking at you. Before you have questions, I'll write down something and everyone can start thinking about it. If you ask Wikipedia, there's a Wikipedia page about integral of log, integral of tangent. If you Google what is the integral of tangent, it actually gives you a different result. So your job is to be frustrated all the time. I already mentioned that. How come Wikipedia says that integral of tangent is natural log of secant x plus c? Think about this and I will accept questions. Right now, questions. Ask me questions about tangent. Did you get it? Tangent. That's getting a bit more complicated and your homework is next level. Oh, not too bad. So how do you think they got ln secant? Yes?
Say you 1 over cosine u.
Okay, I like that. 1 over cosine. So secant is 1 over cosine. But how did they get 1 over cosine then? We have just cosine. Who knows?
Cosine power -1.
Cosine power -1. And where did -1 came from? Here. So it's interesting. They use two properties. Property number 1, log property. If there is a multiplied by log of x, this a can jump into the exponent. So it's going to be ln x to the a. So they use this with a negative sign. Negative ln, absolute value cosine x plus c became ln absolute value cosine x to the -1 plus c. And then, since cosine to the -1 is 1 over cosine, it ended up to be natural log of secant x plus c. This is not very important to know, but I have 2 points to say here. A, you will Google lots of things and they will give you different results. You shouldn't feel scared. You just need to know properties. And this is a good review of properties. And B, some people in this class, or maybe even many, are international students, just like I used to be. So I need to tell you that Americans created the secant thing, secant, cosecant. Everyone else actually not using it. Well, maybe they do now because of you guys. But the thing is, then you need to know it. So let me write it down. Secant x is, as now you know, 1 over cosine x. Cosecant x is 1 over sine x. Even though cosecant sounds like cosine, it's not 1 over cosine. And secant sounds like sine, it's not 1 over sine. So some student explained to me, you should remember if it starts with S, it will be C. If it starts with C, it starts with S. Nice way to memorize. So it's not very logical to me, but okay. In our countries, we just keep it as 1 over sine. We don't bother to mention them. We don't name things like that. So now you know, that since it was an important note to make. Moving on. Definite integrals. The thing is, okay, now we know how to do substitution, but what should we do if we're working with definite integrals? And I hope you review definite integrals because I did give you the review before the classes started, so I hope you did, because we're jumping into it right now. Integrals. The whole month will be lots of integration. We'll be integrating a lot and using trigonometry, which all of you like so much. So what is going to happen if we integrating from 0 to 4 as square root 2x plus 1 2 dx? This is a completely new example. New example. That's called example 1. Has nothing to do to previous examples. It's a square root of 2x plus 1 times 2 dx, but from 0 to 4. Remember, indefinite integral give you the answer as the function. Definite integral should be a number. It's a value. Definite integral is so how far you are? Oh, 55 miles away. It should be a finite result. So if you get a function, you messed up. You forgot what definite integral is. Okay, let's start the procedure the way we know. Let's choose something to be u. What do you want it to be u? 2x plus 1 is a good choice. Thank you. Let u be 2x plus 1. Then du will be 2 dx. We know that. Now, we need 2 dx, and we do have 2 dx. So we don't need to solve for anything. We have the tail is a perfect match with du. So the integral becomes integral, can you tell me? What's the integral in terms of u? Square root of u times du, exactly. But then now, what is happening with 0 and 4? That's like the whole point to learn right now. The thing is, you're not supposed to keep it 0 and 4. Remember, integral has a specific notation. Integral sign starts like so. There's a stuff going on inside, which called integrand. And then there's the finishing point, dx. And we know the beginning, the end, the integral, the dx part, dt, dm, whatever it is. So whatever is happening here, a and b, they should be in terms of the variable we see in front of you. So if it's dx, it should be x. If it's dt, it should be time. If it's dm and it's meters, then meters. So you cannot change the variable but not change limits of integration. That's why we're going to do, the table will grow longer. That was aggressive. So let's change limits of integration. Change limits of integration. For definite integrals, we will do that. Integration. Let's see. This is the first time you might see this notation. Some of you have seen this before, but I will also explain more on Wednesday. X equals 0 and x equals 4. This is what it means when we talk about definite integral. Because this is dx, we know that the variables are x equals 0 and x equals 4. So when x is 0, let's put a bar, or maybe like then. I like the bar better because it's shorter. U is 2x plus 1. So x 0 times 2 is 0 plus 1 gives you 1. You literally plug in 0. You plug it into your u. More. When x is 4, u is 2x plus 1 and becomes 2 times 4 is 8. 8 plus 1 is 9. So instead of 0 and 4, it becomes 1 and 9. Interesting thing to mention, and I will explain it more on Wednesday. U substitution is a transformation. We're transforming function inside of the integral, so we also transform the location of this function. It used to be from 0 to 4, and we're stretching it into 1 and 9. It's a pretty cool idea. And I will show you practically how it's done on Wednesday. So this now is a bigger box. I usually do it like so. The new integral just happened. And now it's a definite integral from 1 to 9. Reminding you how to integrate definite integral. Square root of u, we already know. It's 2/3. U to the 3/2. But now what? The bar. Do you remember the bar thing? The bar. And you plug 1 and 9. And you have to check before you plug 1 and 9. 1 and 9 should be in terms of u. And indeed, it is u equals 1 and u equals 9. You cannot plug 0 and 4 into u. It's like how many grandmothers are going in the morning to the store. You cannot plug number of stores into grandmothers. Units should match. You cannot plug miles into grandmothers or grandmothers into number of apples they bought. Units should match. So we're plugging 1 and 9 because they're u. So u. So 2/3 u is 9. Okay, do you remember top minus the bottom? That's how I teach. Plug 9, the top, plug 1 minus bottom. So I'm plugging 9. Don't forget all the notation, so 3/2 stays. Minus 2/3, plug the bottom, which is 1, 3/2. Calculate. Do you know how to calculate 9 to the 3/2? Oh, nice. People know. Square root of 9, and it is cubed based on the formula of powers. It is m over, it's usually n over m. N over m. Whatever is at the bottom becomes at the bottom. That is root. And then whatever was at the top goes to the top. That's the formula. So square root of 9 is 3. And then 3 times 3 times 3 is what? 27. And I just have a simplified version. Well, I can write down for you. If you want times 27 minus 2/3. And that's become 52/3. This should be a number. A number, not a function.
That's equal, right?
Yes,
Okay.
equals. Thank you for letting me know. Yeah, if I have bad handwriting, you should let me know. So make sure it's not a function because that's not correct. The other way, some of you will ask me, but what if I don't have to change, right? That's what you want to ask. Especially foreigners, we were taught different way. I'll show it right now as well. It's also correct, but not very liked by local educational system. So I will show it on Wednesday. But what I wanted to say is, when I came to the United States, I was writing equal sign and putting my box over here. An American professor took points because of this notation, even though it was correct. Everything was correct. And I got very upset about this. So it taught me not to take points off if your notation is different, but the process is correct. So learn different notations. You can ask me before the exam. And if I approve it, you can do it. It's fine. Homework, start your homework. You can do everything except number 17, which I posted solution for.